First, yeah. First, I will let you know that this meeting will be recorded, and if you prefer not being recorded, your video not being recorded, you can turn it off. Okay. Yeah. Okay. So today I'm glad to share my research talk with you. It's called an accurate and robust imputation method called mbImpute for microbiome data. So this is a collaboration with our previous group member, Wei Vivian Li, who is currently at the Department of Biostatistics and Epidemiology in Rutgers School of Public Health, and with my advisor, Jessica Li. So first, I want to introduce some background about the microbiome study. So microbiome studies explore the collective genomes of the microorganisms that live in a certain environment. The main groups of these microorganisms include prokaryotes, occur bacteria, archaea, fungi, and viruses. The number of microbial cells on human body is estimated to be 10 times the total number of human cells. And recent researchers have discovered that the microbiome plays an important role in human health. So right now, the sequencing-based microbiome studies have shown the potential of using human microbiomes as biomarkers for disease diagnosis or therapeutic targets for disease treatment. The two mainstream methods for microbiome data collection are 16S rRNA sequencing and whole genome sequencing. Although these two varies in their sequencing technology, the final outcome of those two methods is basically a abundance matrix, which has the 2 dimensions indicating the biology samples and the taxa, which the taxa refers to the operational taxonomic units in the 16S rRNA sequencing and maybe the bacteria of the microbiome species in the whole genome sequencing. And so one important feature of the microbiome sequencing data is the exact amount of zeros. The large amount of zeros could be a result of sample contamination and biologically non-existence. By this, I can use a very simple example. For example, if you are sampling the fecal sample of some patients, and one patient has just traveled to a foreign country, and he may carry some foreign taxa. So for those foreign taxa in the other patients, it will have abundance 0. So that constructs the large amount of zeros. And however, there could be other zeros due to the PCR amplification step and the constraint on the total sequencing depth, which we will refer to as sampling zeros. So basically, our imputation method will mainly focus on correcting for these sampling zeros. So we developed mbImpute method to provide reasonable imputation for potential sampling zeros by using a flexible model that incorporates across taxa, across sample, and covariance information. So after imputation, we hope that our data matrix will have fewer excess zeros, thus facilitating the downstream analysis. We want the existing but undetected taxa abundance to be recovered and provide important biological information to researchers. And we want the result returned by mbImpute be the same form as the input. So here, if the input is a m by n dimensional abundance matrix, we hope that our method will also return a m by n dimensional matrix, and the researchers can directly apply their originally used analysis schemes on the imputed data. So next, I will introduce our method. So first, I'll introduce some notations. So we will denote the taxa count matrix as the bold form M of dimension n by m, where n denotes the number of biology samples and m denotes the number of taxa. So here, the n could be, for example, if we collect the fecal samples from patients, the n will represent the biology sample of this. There will be n biology samples, and it could also refer to those n patients. And we also have a covariance information matrix in the bold form X of dimension n by q, and Q denotes the number of covariates for each biology sample. So the covariates could be the gender of that patient and the BMI of that patient or nationality. And here we will also have the distance matrix both form D in dimension m by m, where each element Dij represents the length of paths connecting taxon I and taxon J in the phylogenetic tree. So the phylogenetic tree depicts the evolutionary relationship between two taxa species. So here, basically, we want to incorporate the taxa evolutionary information into our model. So our mBimpute will process in two steps. The first step of identify likely false low counts or zeros. Those is basically identify those sampling zeros. And the second step of imputation. Okay, so as I have said, the first step, we want to identify those sampling zeros. So here I randomly picked 8 taxa and plot the histogram. So here you can see that it usually has 2 modes. The one mode contains a lot of zeros on the left-hand side, and the one mode that's basically non-zeros on the right-hand side. So we have employed a gamma normal mixture model to fit this kind of bit distribution. And maybe you can see here, there are actually kind of 3 modes. However, we always identify the leftmost mode using the gamma distribution to be the zeros that we want to impute. So then after this, the second step of mBimpute want to impute this identified false zeros. So those are the counts belonging to this bluish area. And we want to impute those values based on 3-way information. We want to.
Can I quickly ask the question?
Yeah, sure.
Can you go to the previous slide?
Yeah.
What's the difference between normal in mixture and normal only? Like.
Okay. Oh yeah. So that is like sometimes if the normal distribution itself is good enough to capture the distribution. So for example, if we don't have the small peak over here, like it's just a normal shape, then maybe use the normal distribution itself will be good enough to capture the distribution of this of the counts or the abundances. So then we think it maybe the zeros is just it's just a result of the biological variations in the abundances. So we will not treat those zeros as the false zeros we need to correct for. Does that make sense? Yeah, for example, I think I haven't included a very good result of here. For example, if here if you think of this, you shift this peak to the left a little bit. So maybe the zero can be viewed as part of the normal distribution. So then even if we fit we have fit a gamma normal mixture, and we think we will use a likelihood ratio test to say to judge if our mixture model really improves the fit of this kind of distribution. Yeah. If that's the case, we will not regard this kind of small part over here as the false zeros. Does that make sense?
So I think that a simple answer would be that we just have 2 models. One is a normal only model, the other is a mixture model. So we're just comparing whether the mixture model fits better than the normal only model.
Yeah, I think I understand it now. Thank you.
Okay, great. Okay. Yeah. And I forgot to mention, those have been pre-processed, and all of these are on the log scale. So we do the log transformation in order to feed the distribution better. Yeah. Okay. Then the next step of mBimpute, try to impute on this identified false zeros I have said on the left-hand side, and by borrowing 3-way information, the cross-sample abundances, the cross-taxa abundance, and the covariance information. So in this cartoon illustration, we can see those it's also on log scale, and if the original count's abundance is 0, we will, after the log transformation, we will also transform it to 0 by adding a pseudo count. So basically, after we identified, for example, if we have 3 samples and 5 taxa, we have identified this cell to be the fourth 0. Then we will impute this cell by borrowing information across taxa in the same sample and borrowing information across different samples for this same taxon. And we will also borrow the information from all the covariates such as gender, BMI, and age, and so on. And then after imputation, the originally close to 0 abundance will be raised to a higher value. So we will do this basically we will impute on all the identified false low counts or zeros. So the final matrix should have less 0 values. And
excuse me, can I ask a
yeah,
question?
sure.
So if you have a non-zero in your taxa value, what is the what's the support of the value? Is it an integer or a real number?
Here, since I have transformed it to a log scale, so it will be a real number. It's not an integer.
But okay, what's the original data then?
The original data is abundance. It's count data, so it's not. It's just integers. Yeah.
Thank you.
Oh, you're welcome. Okay, so basically, so the next so in here the diagram is just to depict what I have shown in this cartoon using math formulas. So we can see that the kappa j actually learns the information across taxa for the same sample, and tau I borrows information for the taxon j for the taxon j across samples, and we also learn from the covariance information. So basically, I want you to keep in mind that kappa j learns information across taxa for the same sample. So here we will have m times m minus 1 plus n times n minus 1 plus n times q number of parameters. However, the number of training sample size, those are the counts we think they are not false 0 or low counts. So this will be, of course, less than or equal to the total number of abundance we have is m times n. So this becomes a high dimensional problem. And so we will use the following objective function in our mbImpute. So basically, this is, it's actually, you can think of it as a lasso regression. So we have employed a squared loss plus the L1 penalties. And so I want you to keep in mind that kappa j, as I have shown in the last slide, it borrows information across taxa. So here is actually where we want to employ the phylogenetic information. So basically here, if 2 taxa are closer in the phylogenetic tree, we want to have less penalty on that. So since djk depicts the phylogenetic distance between taxon I and taxon j. So if those two are more evolutionarily connected, the djk will have smaller value. So however, this doesn't mean we will always like pick on those since in our lasso regression is kind of doing a shrinkage, so it doesn't mean that we will always borrow information from the evolutionarily most connected taxa. It could still be shrink to 0 due to we have all the other parameters. And so next I will show some of the results. So first, because I think as far as we know, our method is first to directly to use modeling approach to impute on the sampling zeros in the microbiome data. So we have compared with some proposed method, proposed imputation method in the single cell RNA sequencing. And you can see here there's a method called soft impute. This is actually matrix factorization method. It is actually a matrix completion method that have been proposed to deal with the Netflix data. So we think that the matrix completion and our imputation has some kind of similarities. So we include this method to compare with the matrix complication method, the matrix completion method. So basically in our simulation, we first simulate a complete matrix. Then we introduce zeros to the complete matrix based on what the pattern we observed in the real data. Then we will perform our imputation method on the zero inflated matrix. And the first criteria is the mean squared error between our imputed matrix and the complete matrix. And the second one is the correlation between the complete matrix and our imputed matrix. We can see like in case of MSE, our method have the smallest MSE, and our method has the overall higher correlation in both simulations. And we also compared the taxa divided by the standard deviation. We can see in the complete data, the taxa mean divided by standard deviation has this kind of shape. And after we introduce zeros, the distribution is kind of distorted. And after employing our mblmpute method, you can see that the original shape has been recovered. And this is actually more obvious in this figure, that we plot the taxon mean and the taxon standard deviation as a scatter plot. And we can see that our mblmpute method is able to recover the original shape in case of the scatter plot of the taxon mean and taxon standard deviation. And in case of the real data, we compared among different differential abundance analysis. We found that combining mblmpute with t-test have increased the proportion of repetitive discoveries in the whole genome sequencing data. So first, we perform our method on the type 2 diabetes data. So here we are comparing with the Wilcoxon test, which has been commonly used in the data generation papers, and the ANCOM, which is especially designed for the microbiome differential abundance analysis. And we compare with ZIMP-GLM, which claim to deal with the zero inflation in the count data. And you can see that with our mblmpute method, we find a larger overlap between different data sets. And also, we have tested the performance of our method on the colorectal cancer data, and using our method, it has also a larger overlap among 4 different data sets. And yeah, so with that, I want to thank to my advisor, Jessica Lee, and our collaborator, Vivian. And so this is only a part of a group, since our group are much larger right now. And so we have, so those are the funding sources for Jessica and our group. So with that, I want to thank all you for listening, and I want to hear your questions and also advices for the potential applications of the imputation in the microbiome data. Thank you.
Thank you. Very interesting talk. Very cool ideas. I was wondering, so one of the key thoughts behind this method is that like bacteria that are, or like taxa that are highly related are more likely to appear in a similar abundance. And I was wondering if you thought about using like ecological relationships instead. Because one thing I'm wondering is highly related taxa might be actually trying to fulfill the same like niche. And so they might compete rather than peer.
Okay, yeah, it's a very good question. So basically here, I still want to talk about how the lasso regression works. So basically it will, the benefit of lasso regression is that it will automatically select those coefficients that the model thinks is important. So basically, why I use kappa JK to learn the relationship among different taxa. However, it may not necessarily be picked out because I still have the tau and zeta that learns the relationship across different samples. So you can imagine if the model automatically have a very high tau I, then the kappa JK will be automatically shrink to 0 if it found that including the taxa relationship did not really improve our model. So yeah, does that answer your question?
Yes, thank you.
Okay. Yeah, listened to your talk last time. I think it's also very interesting.
Oh, thank you. I guess one more question. Would it be
Yeah,
easy
sure.
to replace like the phylogenetic distance with like some other, I guess, measure of relationships?
Yeah. It's easy.
Okay.
Yeah, you can do that. It's just, yeah, you can change the weights basically over here. Yeah. So I think it's very flexible for including, like, because what we originally think about this model is that we want to include more information into our model, because comparing to a single cell, it has like more side information in microbiome data. Yeah.
I have a question.
Sure.
I don't have any comments. I just have questions to understand your method better.
Yeah.
When you have that distance matrix, when you incorporate that distance matrix into the lateral regressions, are you trying to say that if two taxa are close together, which means the distance is very small?
Yeah. They are more like evolutionarily connected. So for example, you know that the microbiome has several kind of, you have the genus and you have it at species level, and you may have it at a kingdom level. So for example, if two taxa are belonging to the same genus, they may have a smaller distance in the phylogenetic tree. They will have a smaller distance in the phylogenetic tree.
Yeah, but you incorporate distance so that, are you trying to incorporate the distance into the regression so that if two taxa are closer together, then the weight of the taxa that's close to that taxa that you're trying to impute, it's going to be
smaller,
higher? Is it going to be higher or is it going to be smaller?
So this is actually because you can see I multiply this djk with lambda. So actually, if the djk is smaller, then this term will be smaller, and so it will be less likely to penalize on this term.
So maybe I can help explain. So the smaller the distance, the smaller the penalty. So the larger the coefficient.
Actually, the penalty, yeah.
Oh, I see.
Because the distance is not directly used as a predictor. It's just introduced as a penalty term. So basically, we will penalize less if two taxa are closer to each other in the phylogenetic tree. So basically, we'll encourage more about the prediction, more of the prediction from close related taxa. That's the idea.
Yeah.
Okay, got it. Thank you. I have another question.
Sure.
And well, unless someone else have questions, then I can stop.
It's okay. I think you can ask.
Next questions is when I guess, okay, well, back to this objective function, when you're trying to the L term, like the arrow term that you have right here.
It's a squared loss. Yeah.
Yeah. It's, I guess when you're trying to, like when you're training your model, right?
Yeah.
You have, I thought that term is supposed to be 0, right? Because you're trying to impute it, and then I guess why is it that you include, if you're trying to impute it, why do you take it as like the, as to put into your arrow terms? Does that make sense? Am I making any sense?
Oh yeah. Sorry, maybe I didn't miss this. I didn't explain it very clearly. So those are for the IJs that's belonging to omega, and the training sample size is actually the counts we believe that are not false 0 or low counts. So the omega are the counts that belonging to the right-hand side. So those non-zero terms. We want to train our model on these non-zero terms and then impute the 0 values based on the coefficients we learned from this lasso regression. Yeah, so basically for this objective we are using is basically try to train those kappa j, tau I, and zeta j. And then for the counts we want to impute, we will then use this these parameters, these trained parameters to get a value for that.
Oh, okay.
So how it's just a loss function. We're trying to train a prediction algorithm. So
Yeah.
we're using the y's which we have non-zero values, or which means we trust their values to build this prediction rule, to train this prediction rule. And then we apply the rule to impute other values we think that need imputation.
Okay. Yeah, I think I get it now.
Okay.
Thank you.
Yeah.
And then, well, no, if anyone else have questions, then
Oh, it's okay.
I should ask. If not, I can ask another question.
Sure. Yeah.
If you go to the part where you use real data,
Oh yeah.
to, like, evaluate your, yeah, I guess, what is the test that you are trying to, what's the test that you are trying to recover here?
You mean the test I'm comparing with? Or
No, like, if
so,
given
but
your data,
yeah, so like all the results here are differential abundance test. It's just, for example, if you have the control samples and the sample, like the patients with some kind of disease, for example, here with type 2 diabetes. So we want to detect all those taxa has different abundance levels in those two conditions. Yeah, basically.
oh, okay,
Yeah,
got it.
Yeah.
And then for the simulation part,
yeah,
if you go back to, and when you say like figure B,
yeah.
what's that correlation?
Oh, it's actually like for each taxa, for each taxon, I compute the correlation with like the complete data and the imputed data. So in our simulation, we will first simulate the complete data, and then we introduce zero inflation based on the real data patterns we observed. Then we perform our imputation method to get the imputed data. So here is the correlation for each taxon, compute the correlation between the complete data and the imputed data.
I see.
Yeah.
Thank you. And then, can I ask one more question if no one else has questions?
Sure, yeah, of course.
What in the first step of the method, right? You're trying to you're trying to feed these distributions into your data.
Yeah.
Right?
Yeah.
I guess, how do you fit that data? Maybe I'm not, like, how do you fit the data? How do you find the good proportion between the two distributions that you're trying to fit?
Oh yeah, it's actually a mixture model approach. I use the gamma normal mixture to feed this kind of distributions.
And
so the key thing is that we're fitting one distribution per taxon. That's the key.
Yeah.
We're looking at, for one taxon, its abundance across samples. So we are expecting that if there is no sampling error, then the distribution should be one mode. But if we see a mode near zero, we think it suggests that it's sampling error that need correction. That's the rationale. So therefore, we are trying to compare a one mode distribution represented by normal only versus a mixture model to see if there's strong evidence suggesting that there is zero inflation. If there is, we want to decide which entries belong to that zero inflation, identify them, and then correct them.
And I guess you just estimate those parameters of the distribution by, like, maximum likelihood, right?
Yeah, right. By the EM algorithm to find the parameters.
Okay.
EM algorithm is to maximize the likelihood. You're right.
Yeah, right.
Okay. Thank you.
Any more questions? All right. Thank you very much,
Okay, thank you for listening.
Ruochen.
You.
Thank you very much.
Thank
Bye.
you. Have a great weekend. Bye.